Everybody. It's my great pleasure to welcome all of our speakers for the tutorial that I believe that they did a super great job. I don't know, is there any chance that we could actually share with all the participants the links to these tutorials, but they must be actually available public, I don't know, later. And we're going to cover three fantastic topics by many actually of your expert people, especially from the EHD collaboration. So that actually include synthetic data generation, VIDA image and model reconstruction, and theoretical simulation. I encourage each of teams to actually to stick with 20 minutes of the presentation, followed by some basically question and answers at the end of the conversation. Maybe, Lindy, we could also actually think of having some breakout rooms afterward in three of them in which people can just go and speak with the speakers. So yeah, I encourage you to stay, especially for those that are early career. I'm sure that you get a lot out of it. So let us start in a benefit of the time with the first topic, which is the synthetic data generation. I think that there are different folks here that are going to actually coordinate it, and each team should have a leader for each of them. So Frank, do you want to start? Please take it away. I can stop my share if you want. And you can just either use your share screen, or do you want me to guide it up?
Well, I'll just share my screen so I can.
All right. Okay.
Get to the.
Please take it.
Okay. Yeah, so I will be starting with giving an introduction to the SYMBA synthetic data generation software, and then after me, Alex will tell a bit about generating synthetic data with EHD imaging. So SYMBA is the synthetic measurement creator for long baseline arrays, and it was written by Michael Janssen and myself. Its approach is a bit different than, for example, EHD imaging, which generates data in sort of a data-based approach, so based on the features that we see in the real data, where SYMBA is trying to model them more in a priori physical way. So the first step that we do there is that we simulate the corrupted data as it would come out of the VLBI correlator. So that means that it's frequency resolved, and it has several corruption effects in there by a model of the atmosphere, and also antenna pointing, offsets, and seeing. And in addition to that, the thermal noise, polarization, leakage, and gain errors that can be added. And then when that corrupted data set has been simulated, it is passed through a synthetic data or a VLBI data calibration pipeline, RP-card. And then you end up with a calibrated data set as you would get it, for example, from the EHD. And then you can use that to reconstruct your source model with imaging or fit, for example, black hole parameters. So this is just an overview of what happens in the code. So the red box here is the master input file, and that really contains all the parameters needed to simulate an observation. And it points to these other files here in yellow, which are your source model, the antenna and weather information, the observing schedule, and you can also put in an actually observed observation so that you can recreate the UV coverage exactly. And from those inputs, you generate an observation, and that we do using the Make Silhouette software, which is calculating the visibilities and adding all these corruptions. And then we do a calibration with RP-card, and that is using the same information that you would also use for during a real observation. So from the information that from the corruptions that Make Silhouette applies to the data, we generate an on-top table that is then used to do an amplitude calibration, and also we do a fringe fitting of the data. So then in the end, you get this calibrated observation, and then there are a few optional steps such as flagging the scans that were not in the actually observed observation. And then you can do a network calibration using the EHT imaging software. And we also include an EHT imaging image reconstruction script so that you can go all the way from a ground truth source model through a realistic observation and then a reconstructed image in one go. So I'll tell a bit about these effects that we're adding. So the atmospheric effects are split into two types. There's a mean troposphere that's causing a time delay, attenuation of the amplitudes, and also emission, so in the form of sky noise. And then there is a turbulent troposphere, which gives us these rapid phase fluctuations with coherence time of the order of 10 seconds. And the Maxilloid software is using ATM to simulate these mean tropospheric effects from weather parameters. And you can get these weather parameters, for example, from the VLBI monitor that is used for the EHT or from radio climate modeling. And the parameters are the ground temperature, the ground pressure, and the precipitable water vapor. And then for the phases, we use this phase changing screen with Kolmogorov turbulence on the time scale based on this input coherence time. And on the right, you can see an example for some stations, how this turbulent phase evolves as a function of time. Then we're also adding these antenna pointing offsets. And to do that, we model the telescope beam as a Gaussian, and then you can give an RMS offset in arc seconds, and you get, and then two types of offsets are simulated. There are short-term offsets caused by the wind and seeing on the time scale close to the coherence time, and there are long-term pointing offsets that are caused by inaccurate pointing solutions that are degrading on the time scale of a few VLBI scans. So I'll go through some instructions for getting SYMBA to run and go through the input files quickly so that you have everything you need to get started with the software. So SYMBA is hosted on this Bitbucket repository. You can download it from there. If you want to install the source code locally, that could be a bit time consuming because it has a lot of dependencies. So it is probably easier to use the Docker image so that you can use this pretty much right away. And you can also use Singularity for that. And the instructions for doing that are all in the README in the repository. So I'll now try to go through this master input file quite quickly to give you an idea of what the parameters that you can set. So I've highlighted a few of them here. The first one is the working directory where your output files will be created. So you can just give a path here and then everything will be done there. You have to point to the antenna table where you have all the antenna information. And there's here's an example of the parameters that you can use. So this is a text file where for each antenna, you give the position, diameter, aperture efficiency, the receiver noise, and then these gain and leakage and pointing parameters. And also for each antenna, you can put in these weather parameters. And we have an example here in the SYMBA repository. And for an ngEHD observation, there are also antenna files released with this second analysis challenge. So if you want to simulate an ngEHD observation, you can get that from there. So what you can also do is follow an observation that has been defined in a VEX file, as is done for the EHD observations. And you can point to that here. And here you can then put in your source model. And for the source model, there are a couple of formats that you can use. there you can use fits images, and anything that will work with EHT imaging will also work with SYMBA. You can also use the EHT imaging text format for an image or a max silhouette text model. And this is basically a list of some Gaussian components. For polarized models, there's this input visible parameters that you have to set it through. And you have to use this file name convention for the IQ, UNV models. And for time variable models, you can put in the frame numbers in this way, and here in combination with the polarization. And for the time variable model, you also have to specify the duration of each frame here. There's also here this option to do a network calibration. Here an option to match the UV coverage of an actually observed data set. You can set the frequency setup, so you can set the bandwidth and the number of channels. And then if you are not using invex file, you can also build a custom schedule, but then you have to set the coordinates of the source. And here you can put in the start time, the length of your observation, the number of scans, and the lag between each scan. You can set here the data integration time, and you can turn on and off these atmospheric effects and different components of that. Here also for the pointing offsets and for the gain errors and the leakage. And then finally, there are some parameters for the calibration. So if you're adding all the corruptions, you can just leave this rpcard full pipeline to true, and it will do all the calibration automatically. If you're, for example, simulating a data set with only thermal noise, you don't need to do a fringe fitting or amplitude calibration. You can set this to false and set the steps that will be done instead. And finally, you can there's an option here to make an image, and also to keep all the raw simulation data that is created by max silhouette. Yeah, you can try to run a SYMBA simulation yourself. So the first step is to download and run the Docker or Singularity container. And you can follow the steps in the README in the SYMBA repository for that. And then in the documentation, in this section 4.3, there are some instructions on how to actually run SYMBA. And if you do that, you can, what you will do is you will start from this model of M87. And if everything goes well, you can get out this, this reconstructed image out of that for an EHT 2017 observation. So that's it for SYMBA. And I'll now hand over to Alex, who will tell a bit about EHT imaging.
So EHT imaging is a set of Python objects and has a lot of very nice capability. I think later in this session, folks will talk about imaging. It can be used for synthetic data generation, and you can read more about this tool in Andrew's 2016 paper and subsequent references. It's available at GitHub at the link below. Frick, I don't know if you're in charge of the slides or Razieh. Thank you for advancing just as we go through these. So there are some nice example scripts that are included at that GitHub link. And just to show how the process works, you begin by loading a source image, and there are some source images available in the distribution, or you can use your own. And so this object, IM, you load it and you can display it or print it out. And you can look at attributes of this object, for instance, the source position, the RF of the source, and so forth. Next, you can sample the image with an array of your choosing. You load the array, and like SYMBA, that contains coordinates of the stations and other details that you're able to specify in the array file. And again, you see examples that are included in the distribution on GitHub. Third, you can set settings for an observation, and it's as simple as im.observe with a few parameters to generate an obs object. The flags that go into this im.observe, you should pay attention to closely. You can, for example, have amplitude calibration or phase calibration turned on and off, and several other settings, which you can control through this one line. Finally, you can output your synthetic observation into a UV-FITS or a text format as you like, and then have it available to you to analyze later, for example, in an imaging step, which will be covered later in the talk. It's a very nice tool. I encourage you to take a look.
Okay, thank you so much. That was really on time. I think that we have time for one or two quick questions, or maybe we can even postpone them to the later, actually. But is this any very quick question for now? Okay. All right, maybe people are actually expecting to ask their questions later on. Right, I don't see any raised hand. So can we actually go, okay, let me share my screen very quickly then. So now is the time for going to the second theme, which is actually about VLBI image and model reconstruction. So we have a number of fantastic speakers for us. I think that Raman is going to lead this conversation. So Raman, do you want me to stop share and just you do it?
So sounds good, Razieh. Either way. Thank you. Yeah, I'll take the first few minutes and then I will hand it over to I believe Antonio, who will then take you on a ride with EHTIM generating some images. Let me know if you cannot see this all right, or if there's some Zoom
Sounds
windows
good.
in the way.
Yeah, that's good.
Great. Okay. Yeah, I thought it was a good idea to, given that not everybody on the call is part of the EHT, to remind people a little bit that before we get to the stage where we can really scientifically analyze the data and do image reconstructions and all these things, there's a lot of steps that have already happened to the data, which is why tools like SYMBA and EHTIM are so useful, even if you are, for example, a theorist trying to make a prediction and you're trying to get into these questions of how can I compare this to measured data and so on. So this measurement is of course very, very complicated, and each and every step introduces a certain amount of uncertainty, and so it's very important to follow that data path and that calibration path as closely as possible and understand that. So there's this correlation stage, there's various calibration stages, and only after that, after several orders of magnitude of reduction in data volume, are we then able to do things like the image reconstruction that you've all seen, for example, for M87. And so you'll see these algorithms in action very soon. But keep in mind that there is an entire very lengthy and very laborious process involved that is not perfect, of course. Right. So here you see some of the steps of the stages of calibration as applied to the M87 data set. You can see here after phase calibration, this is how the signal to noise plot as a function of baseline looks like. And now if I flip through after a priori calibration, looks already much tidier. And then after network calibration, you can see the differences here. So just to give you a flavor of the kinds of evolutions that these data sets undergo as we go through the cycle. And then once it's ready for scientific analysis, this is then what we're dealing with. And you can see already the features, and we've overlaid a uniform ring model here, so there's already some features you can pick up. And then we can really get into imaging and what is imaging. So you can view imaging as one way to do model fitting. You can think about an n by n pixel image, and each pixel is allowed to have an independent flux. That's a little bit simplified, but that's how you can look at it. And for each combination, you basically sample through the space and compare to what you've measured. And at the end of the day, you can see, as you take more and more data into account, the image that you reconstruct is of course then getting better. And it really shows you, going through these examples that you'll see with the HTIM next, how this gets done. Before getting there, there's a list of various packages that are now available. There's of course ngEHT imaging, which has been around now for quite a long time and is coming up next in this tutorial. Has an enormous amount of useful features that you hear more about in a second, and that was of course used, like Smiley, in the ngEHT M87 papers that had such a large impact. ngEHT imaging I've used myself. I find it very useful and very easy to use, so looking forward to that part of the tutorial. But there are other imaging packages as well. CASA, DivMap, more recently Themaging as well. I'll try to capture that a little bit later, and other algorithms as well. So I'll hand it over to Antonio here to do the ngEHT imaging.
Thank you, Rowan. So
should I keep going, or do you want to share the slides?
Yeah, you can keep going. Yeah, no problem. All right. Yeah, so I don't have much time. So yeah, let's go directly to this. Can you still get the previous? Yeah, sorry. Yeah, so rather than a very generic tutorial, this is going to be an applied tutorial for imaging the challenge 1 data that was released some time ago, and that Frank mentioned during the meeting in some early days. So yeah, I encourage all of you to participate in the challenge and to take a look at the GitHub of ngEHT imaging, which is linked there in this slide, and to the Jupyter notebook and the data that I will present here today. It's also hosted in the GitHub that was shared before. Yeah, please take a look at the ngEHT imaging GitHub, and there is a very nice documentation there. You can learn a lot of things from there. So yeah, next slide. Okay, so you will start as you do with every different software. You start by loading your observations. You can load in the UEFITs, or if it's text files, so there are plenty of options. And then you will spec your data. So there are a lot of functions to do this. You can plot your UV coverage, shown here in the left. You can plot your visibility amplitude as a function of the UV distance, as you can see here on the right. You can plot visibility phases, closure quantities, phasing, closure phases, closure amplitude, single baseline, many different things. So as you can see here for the amplitudes that are plotted here, so this data set that I will image today here in this tutorial contains only thermal noise and atmospheric phase corruption. So it's rather a simple data set, but it's pretty nice for learning ngEHT imaging. So yeah, next slide, please. All right, so you then will do some data averaging, which means that we will do some, for example, some time averaging. So for this particular case, we will do a scan averaging. So we will average each scan. We will not do like 60-second averaging or some other time interval like we usually do when we do some imaging. But this is, this data set, as I said, is rather a simple one. So scan averaging is fine. And then there is another quantity that's very useful for imaging with ngEHT imaging, which is the zero baseline flux, which can be measured as the median value measured by the intra-site baseline, like ALMA apex. And then you can also define your array nominal resolution, which is just 1 over the maximum projected baseline that you have, distant. And then you will also define your non-closing error budget, which in this case with 1% is not. And if you, so we are imaging now MET7, but let's say you want to also image say J-star, which is a data set that is also present in the challenge 2 that was presented some days ago. Then you maybe want to do some scattering also that will be done here. And now we just do a copy of our observation before we do any self-calibration and so on. So we can then self-calibrate our data to the final image at the end. Next slide. Okay, so now before we start with the image reconstruction, we will define a prior and initialization image for the algorithm. So the prior is very important for maximum entropy regularization, and then in this case the initialization image will be the same as the prior. So this initialization image will be passed to the algorithm, so the optimization will start from that image. As you can see here on the top right, this is the prior that we will use. This is a very particular prior because we knew beforehand what was the model like. So we knew that there was a very bright emission around the shadow, and then some extended flags to the northwest. We knew that there were no flags to the other side, so that's the reason we can use this very particular prior. But I think it illustrates very well how you can play with different priors and add different geometric model to your prior to make it a better guess for the algorithm for imaging. So yeah, there's a Gaussian on the left bottom corner. There's a large piece to capture extended flags, and yeah, so that's basically our prior here. Next slide. Okay, so now we start with the image reconstruction. So first we define the data products and the regularizations, the regularizers that will be used for imaging. So one of the very good things that each imaging can do is use full closure quantities together with closure complex visibilities during the imaging to constrain on images. So in this case, since we know that the phases are corrupted, we will use just amplitude, closure phases, and log closure amplitudes, all of them with the same weight. And then to regularize on our image properties, we will use the TV and L1 norm regularizer, which favor smoothness between adjacent pixels and sparsity respectively. And for this particular case, we won't use maximum entropy regularization or TV2, but I encourage you all to play with these regularizers and to see what different images you get when you change these values. So we start our imager, which is this function you see here, by passing our observation, our initial image, our prior image, which is the same, the zero baseline flags, our data products, our regularizers, and some other parameters. So when we now start the optimization process by making the first image, and then after it finished, we will get one image that it resembles more or less the ground truth image, and then we will use that image. We will blur that image to the nominal resolution of the array, and we will use that blur image as initialization in the next iteration, in the next imaging iteration. We do this to help the algorithm escape some local minima that it could find during the optimization process. So we will repeat this process of imaging and blurring the output image several times. In this case, it's 5 times. And then we will self-calibrate our data to this final image that we've taken. Next slide. So this is an example of the kind of images that we are getting during the process. So we start with this image that you see on the left, which is the initialization image that we define. And then after some iteration, we will come to this image that you see in the middle, which looks very similar to our ground truth image already, but still we are not seeing any extended flags that we know it's there. And after some more iteration, we start to lose some of these diffuse flags, which is not real, and then we start to get some of the extended flags, but still we can do better. So next slide. So now that we have self-calibrated our data to this previous image, we have recovered phases, so we can incorporate to our data products full complex visibilities. So we are updating our initialization to the previous image floor to the nominal resolution. And then we add complex visibilities, closure phase, and log closure amplitude, and increase the weight of the data terms a bit, because we trust our data more now. And we repeat the imaging process that I just described before. So, next slide. Okay, so this is on the left. This is the image that I showed you before, the final image that we got in the previous iteration. And here on the middle is the final image that we obtain when we incorporate full complex visibilities and do some more iterations of imaging. And you can see on the right how it compares to the ground truth image. So it's pretty similar. Yeah, next slide. All right, and then we can, when we are done with our imaging, we can save the image that we obtain. We can save the self-calibrated data. We can plot the image in different ways, logarithmic scale, linear scale, with different plotting style. And we can also generate a PDF with a summary of the statistics of our image, a lot of plots showing the fitting of our image to the data, for closure quantities, for amplitudes, for phases. This is a very piece of information, and it's really useful to us to get a sense of the quality of the image that we have reconstructed. And next slide. Yeah. So, but anyway, I mean, this PDF is really nice, but if you want to take a quick look at some of the data quality quality of the image that we obtain, you can do some quick plotting, comparing your self-calibrated data to your image, like amplitudes as a function of UV distance or closure phases, as you can see here. But many other options are available. And yeah, this is the end of the tutorial. Thank you.
Do we want to take questions, or should I go ahead with the Themis part?
I think that we may be lack of the time. Can you please, as I said, we may think of having some breakout rooms afterward, and please put all of your questions in the Slack channel so we get back to them. I apologize, Sarah, but I think we are very much tightened of the time. Please go ahead.
All right, I'll push through. So let me mention that there's a couple of other modeling packages available that in some detailed areas go beyond image reconstruction quite substantially. I will be talking about the Themis package, and we'll later hear about the Rose package and also DPI, I think. So the Themis framework is a little broader than what you heard about the EHT imaging in the modeling sector. It's not doing simulated data, but what it does is it attempts to be a framework in which all the interfaces between things like data, models, and samplers and so on are very clearly identified and defined. And that sounds very dry at the beginning, but it has proven extremely fruitful, because now within a couple of years of development, not too many years of development, this package has really grown into a very impressive suite of tools. So getting these things nicely modularized and make them very extensible has allowed us to combine various different features that were developed more or less independently. And then every component can take advantage of developments taking part in another sector automatically. And that leads to a super exponential development. What a wonderful word. Just to highlight some of the things that it can do, and it's really impossible to summarize it all. You can think of it as the geometric modeling things that people in radio, VLBI, and other areas of source reconstruction and astronomy have been doing for a long time, where you can take rings and Gaussians and all these things, let it loose on the data. So that's shown on the left. It has imaging capabilities quite recently, since last year, and can also handle polarization data. And this is an example where the polarization work was implemented, and then it could naturally more or less take advantage of the imaging capabilities. And Paul, who's also on the call, you will hear more from him next, has also tremendously improved the sampling capabilities in Themis, and these samplers are really are really fantastic. You can also see on the right an example of a time-dependent semi-analytic model where you have either like a RIAF solution and hotspots flying around, and all of this is part of this package. So you can see there's quite a number of things going on, and I will not go into the details, but there's a substantial number of things existing already, and the idea being that if somebody new wanted to contribute, all you have to do really is to provide that new feature, without necessarily reinventing the wheel. If your model can provide visibilities or something, then there's no need for you to code up how to go from there to closure phases, or how to compute closure amplitudes or so on. You don't have to worry about it. All you pass is the visibility, and the rest that's already coded up in Themis is doing the work for you, and all of that. So it has a number of other things that you normally would have to work out yourself if you were to do it from scratch. And this is like gain solvers, for example, if you want to fit complex visibilities or visibility amplitudes, if you want to do scatter mitigation, polarization, and so on. So there's a lot of things that are being taken care of for you. Right, so here's an example. Any parameter estimation tool can, of course, produce these triangle plots where you see the posterior distributions and correlations and the parameters and so on. And you can apply this now to different data sets and yeah, do these very nice quantitative inferences of parameters across the board in a very versatile manner. Some funny exercise, you can use a tool called SLOC count that counts the standard line of code in Themis, and I've taken the liberty of just looking at our development branch, which is only one of many branches that we're using, and you can see the output on the right. So it has about 130,000 C++ lines of code, quite substantial development, and the expectation is that we should have 17 developers. I can tell you that's not true. That was never true. But it's it's a substantial piece of code, and it can do a lot of things, but we can always use more help. So if you want to contribute, we are working on making this code public. It is not yet public, but we have some bare bones version lying around. If you want to try that out, please get in touch with us. One thing we're also proud of is that it's designed to be run on supercomputers. It has various degrees of parallelization, and we're beginning to utilize the GPUs as well. So that's pretty fresh. And just to highlight an example, so this would be one of your main files that you would use to drive an analysis. It's somewhat simple compared to what we use on an everyday basis, but it illustrates essentially most of the tools you need. There's a couple of include statements that are basically always the same, that you don't really have to worry about. And then the rest is very simple. You read a data object in, you make a decision on what data you want to fit, you make a decision on what model you want to use, and then you choose a sampler and make your likelihood to your one complex visibilities or so on. And that's really it. So the main file, at least on that level, is kept fairly simple. You specify your priors and so on, and then you just hit go on the sampler, and it will do all the work for you, produces output that you can then visualize with a tool called ThemisPy or any other analysis package that you would like to look at. All right, that's all I had. On to image analysis and feature extraction.
Thank you so much. Again, I apologize. We are very lack of the time. Jacob, please have your question in the Slack channel. We may have some time for question and answers afterwards. So, Paul, are you going to present?
Yeah, I'm ready.
Perfect. Okay.
Okay, so I'm gonna talk a little bit about image analysis and feature extraction. This is kind of goes in line with imaging itself. So if you go to the next slide, Razieh. So imaging is really like one of the first steps we need to do when we look at ngEHT data. So you have the image of M87 on the left, 3C279 in the middle, and then the recent SENE results from Michael Janssen. And well, these images are amazing and show us a bunch of stuff. What we're really interested in is quantitative features about the images themselves. So next slide, Razieh. So for instance, the image of the black hole, you might be interested in something like the diameter, the width, and the position angle, because these might be tied to specific physical parameters of interest. For 3C279, maybe the brightness of the central core versus the central second emission and the orientation of these two ellipses. And then maybe for Sen A, you'd be interested in the kind of this like opening angle of this fork here. And so to deal with this, we have a couple of tools in the ngEHT. The first is Rex. If you go to the next slide, Razieh. Which is this tool is a part of EHT imaging itself, and its sole focus is to extract ring parameters. So it does this by identifying the center of a ring and then taking average azimuthal profiles to construct things like diameter, width, brightness, maybe the fractional dispersion of the flux. And this has been used to great effect, specifically in the first M87 results in papers 4 and 6, and in future analyses. The other main tool that we have for this, if you go to the next slide, Razieh, is VIDA, or Variational Image Domain Analysis. And what this does is it takes a little bit of a different approach. This works with any image structure, and it kind of does template matching. So if your image reconstruction looks like the image on this image on the left of this so-called double ring, you may be interested in a number of different things. If you're just interested in the diameter and the width, you can fit a Gaussian ring to it and get this result. If you're interested in just a general brightness asymmetry, you can fit something with a slash. You can also fit something with asymmetry, maybe asymmetry and slash. If you really think the second ring-like feature is important and you want to characterize it, you can fit 2 rings, and you can fit this like bumpy profile as well. And the nice thing about this approach is that you're not restricted to rings. You can fit any image on the sky, and you can fit any parameterized function. So if you have a image model of what a jet looks like, and there are physically interesting parameters, you could fit this to the image as well and extract those. Next slide, Razieh. So how VIDA works is, I don't want to get into this too much for running out of time, but it's a pretty simple little thing. It's written in Julia. It's written in Julia just for speed reasons. This has been pretty heavily tuned to be quick, but a typical script just looks like something on the right. It's you just load the image, define these templates that you want to fit, and then it's just a single line to define this like optimized template. And there's a couple of resources for these. There's the notebook at this GitHub repo, and then as well as there's additional examples in the docs. And if you run the notebook in this first link here, you can take that image reconstruction that Antonio had developed, and then you can kind of try to extract the ring diameter, and then also this like secondary jet feature as well. That kind of you can see is matching this larger scale structure. And so I think that's everything, and we'll move on to the next group.
Thank you so much, Paul. That was really fantastic. So I think that, yeah, so Roman, do you want to actually stop your sharing? I think Paul is going to lead the other part.
I am trying. Hold on.
Okay. So Paul, please take it.
Yes. All right. Yeah.
I think you're grading on time. So Team 3, I think you have about 20 minutes for this presentation. Yeah, go ahead.
Okay. So, all right. Moving on a little bit, we're going to move a little bit further from direct analysis with data and onto theoretical simulation. And so this is going to be an information-based presentation, and it's going to be led by a bunch of people. We're going to start with Ben Prather talking about an overview of what it means to do a theoretical simulation.
Yeah. So I'll try to be sort of quick with this, but the codes that you've seen so far are part of a larger pipeline if you're trying to evaluate theoretical models of any sort. So this starts with initial system parameters like the black hole spin and magnetic field. So I'm starting over on the left, and the pipeline in general, the arrows generally mean the outputs from one thing become the inputs to the next. So these black hole spin and magnetic field parameters become the inputs to GRMHD simulations, which provide as their outputs fluid descriptions. So GRMHD is general relativistic magnetohydrodynamics, and these are, as I'll describe in a sec here, just forward simulations of the equations from first principles, starting from a torus and ending up with disk accretion state, just some sort of steady state accretion. And so they output 3D distributions of what are called the fluid primitive variables, so density, temperature, velocity, and magnetic field. And then those are, so when I say temperature, that's the temperature for a single fluid. GRMHD simulations are single fluid simulations. And so we have to, from a single fluid temperature, derive a temperature for the electrons via some model. And then that becomes one of the inputs for GR ray tracing. So general relativistic ray tracing, where we take a camera and trace back lines of sight for each of the pixels. So this is dependent on, of course, the camera positioning and parameters like the inclination and so on, as well as the electron thermodynamics, right? How we're deriving this electron temperature or electron energy distribution function from the fluid temperatures, from this, the 3D model distribution, either from a GRMHD simulation or, right, you can derive analytic approximations of these as well. So from images, you can calculate overall image integrated observables, like were used in the M87 polarization paper, right? So an overall zero baseline polarization or total flux, or all of these sorts of things, or as well simulate detector responses. So given an image, right, some distribution of intensities on the sky. These are the simulations you've been seeing so far are largely the simulations of detector response or particular coverage in the UV plane of EHT or ngEHT configuration. And so from there, as all of the analysis and such. All right, so this starts generally, again, this is analytic but generally starts with GRMHD simulations, which are direct forward evolution of the equations of general relativistic magnetohydrodynamics, and generally are run, or at least for EHT purposes, have been generally run in libraries over the black hole spin parameter, this A star, which we range from -1 to 1. So the black hole spin parameter magnitude ranges from 0 to 1, but we simulate both co-rotating and counter-rotating black holes, and then over the phi parameter or magnetization of the disk involved. So this can be a magnetically arrested disk or a standard normal evolution. Simulations are the two sort of general states that we come up with. So there's sort of this cutoff in disk magnetization that generates these two sort of final states as simulations progress. Generally, these are quite computationally intensive, right? You've got a 3D grid of different cells, and have to evolve it for tens or hundreds of thousands of dynamical times, and these produce, as I said, a series of snapshots of fluid state. So this is density, temperature, magnetic field. So a bunch of different codes exist for generating these simulations that we'll talk about at the end. However, since they're pretty computationally intensive and also fairly complex, so beyond just time considerations at this point, the reason we're not just showing you input decks directly is your best bet for GRMHD simulations is likely to start by working with someone who's already in that space, right? Or otherwise sort of start into this systematically, rather than giving you an input deck and assuming that the simulation you get out has much meaning. Okay, so with that, onward to GRRT, which George Wong I think will present.
Thank you so much, Ben. That was super great. Yeah, so George, please take it.
Okay, great. Can we go to the next slide? All right, so just to provide a bit of physical context for what we're talking about here. So as Ben wonderfully described, the output of these GRMHD fluid simulations is a set of fluid snapshot files that describes the state of the plasma over space, and it's a time series, so it describes it over time as well. And for sources that are particularly relevant for the Event Horizon Telescope and for frequencies that are relevant for the EHT and the ngEHT, the primary way that we see these things is through synchrotron emission at the 230 gigahertz frequency that we're looking. And so again, just to provide some kind of physical backing or background for people or to remind people, synchrotron radiation happens when you have electrons that are moving around magnetic field lines. And so the acceleration around magnetic field lines produces some radiation that is in principle polarized. So the electric field that's oscillating has a particular direction of oscillation or orientation of oscillation. And the purpose of ray tracing codes is to kind of track the synchrotron radiation, both as it is emitted, but also as it propagates through the plasma in the accretion disk. And I want to just remind everyone that when radiation that's polarized propagates through a magnetized plasma, it can undergo Faraday rotation. So if the propagation speeds for one direction are different than for another direction, then you might have some overall twisting of the orientation of the electric field. Of course, we're doing everything in general relativity. So you also have to take into account the fact that derivatives are a bit more complicated. And so the purpose of ray tracing codes is to both model this emission and model the effect of plasma as electromagnetic waves propagate through it, and also to take into account the geometry of spacetime via GR or extensions to GR. Next slide. Okay, so there are two different kinds of observables that we produce. So there are images and spectra. I'm going to talk about images really quickly. And in particular, I'm going to focus on this IPOL code, which produces images, though there are, of course, plenty of other public resources. So other codes other than IPOL that produce images, and there's a list at the end. I just happen to be most familiar with IPOL. The basic idea for all of these codes, though, is that you can trace a bunch of light rays back to the camera and figure out effectively which light rays are important for an image at a particular point in space, right? You don't want to waste time figuring out what happens to photons that end up not at your camera. So that's what I'm kind of showing you here on the right side of the diagram. You imagine that there's some camera that's placed infinitely far away to the left, and you figure out what all of the rays that would intersect with that camera would do when they get close to the black hole, and you take into account general relativity. So mass bends these light rays, then the light rays end up crashing into the black hole object, and so on and so on. And then you take this geometry of light rays, and at every single point along that light ray, you figure out what the local emissivity is, what the local absorptivity is, what the rotation that you would get from Faraday rotation would be, and you solve these equations. So it's a set of differential equations. I have not included the equations on this slide. If you are interested, you can, of course, look at all of the resources. But the basic idea is that you're solving a bunch of differential equations, first to figure out the locations of the geodesics, and then to account for how emission gets added to each light ray, and how emission intensity is attenuated, and how these rotational modes may change. And at the end of the day, you get something like what we're showing here on the bottom, and in particular on the bottom left. So you have the overall intensity of light at every single pixel. You can change your resolution however you want, and that's shown in grayscale underneath everything. And then also at every single point, you have this description of polarization. So what is the orientation of the electric field that you would see if you were just looking at that particular pixel? And also how much of the total energy that you're receiving is in this neat ordered oscillation mode of the electric field. And of course, you can break this up into different kind of views. So you can just look at the total intensity. You can look at this fractional linear polarization, how much energy is in the polarized mode. You can look at the orientation. You can also look at circular polarization modes. And again, the output of these polarized imaging codes is effectively a bunch of 2D arrays telling you what is the total intensity, what is the intensity in linearly polarized light, what is the orientation, and so on. So kind of breaking from the trend of previous presentations, we have not included a bunch of step-by-step code screenshots here, but instead we have a quick start available online at that link. And of course, we are happy to answer any questions about the code, help you get started with it. So these are our emails. If we can go to the next slide, taking account of the time. The other thing I said that you can do is, instead of producing images, produce spectra. Here for spectra, in addition to absorption and emission, so spectra meaning how much energy you get as a function of frequency. So in addition to absorption and emission, you also might care about scattering. So through a scattering process, the photon can gain energy, change frequency, and so on. And here, GRMHD, which is the code I'll be talking about that produces spectrum, GRMHD is different than IPOL in the sense that for IPOL or for imaging codes, you only cared about certain directions, but here for GRMHD, you really care about the entire domain because you don't know how scattering will realign your angles and so on. So GRMHD is a code that does this. It loops over every single zone in your computational domain and figures out what the emission is there, and then it solves, in principle, the same equations. You're just you're having some emission at every single step along your geodesic. There's some absorption, and there's some probability that you will scatter. And if you scatter, you create a new geodesic, and you trace that all the way out to infinity. And at the end of the day, you have some distribution of energy versus frequency. If we can go to the next slide. So again, there is a code walkthrough available online. Here, I've linked explicitly to a tutorial PDF that we produced earlier. Again, if you have any questions, feel free to email either myself or Ben. And one thing that I just want to point out for codes that deal with scattering is that they can be rather finicky. So if you scatter too frequently, in terms of just numerically, if you allow your code to scatter too frequently, you can crash your computer system by running out of memory. And if you don't scatter enough, again, this is a detail of the numerical implementation, you can get a very noisy result. So there's this so-called ratio bias tuning step that goes on. Again, this is all detailed in the tutorial PDF, but the upshot of this is that I really strongly suggest, if you're interested in running GRMHD, that you run through those tutorials step by step, because hopefully that will teach you about the nuances of scattering and how to deal with the biases. And as I said at the beginning, we're both happy, Ben and I, to answer any questions via email. And now, if we can go on to Daniel.
Thank you so much, George. That was very nice talk. And yeah, I encourage everybody to contact George and Ben. They are very good and patient people. So yeah, Daniel, please take it.
Great. Hopefully you all can hear me. Judging from the transcript, it looks like the answer is yes. So can you please go to the next slide, Paul?
It's very quiet, Daniel. We can't hear you, but it is quiet.
Interesting. I got that feedback earlier today and boosted my outbound by 500%. Hopefully that helped. In any case, I'll speak up. So I realize we're already past time. So this is just sort of an info hub, because I don't think going through code here is really going to stick in people's brains. But given an already ray traced image of GRMHD, you need tools to actually manipulate it and analyze the properties of the image that are informing your observables, or your takeaways, or your theoretical predictions. And EHT imaging, as has already been mentioned at great length, provides a comprehensive toolkit for dealing with FITS images, H5 images, text files, whatever format is useful to you. And so beyond the sort of reconstruction capabilities, it's also a very natural platform in which to compute image properties of interest to theory. So in particular, the EHTC papers 7 and 8 computed a number of observables related to essentially how polarized the image is, where the polarization lives, and what the pattern of the polarization tells you about the magnetic field. And so I've compiled a GitHub repo that goes through essentially the minimal example of how to compute all of these properties for an image, in addition to some other basic image loading and blurring and regridding things. So if you could go to the next slide, Paul. If you get any takeaway from this, I hope it is that it's really not hard to do this. It's very user-friendly, as others have said. This script that I've uploaded on this GitHub is 35 lines, the majority of which are comments. It's really quite simple to get all of the information of relevance to existing EHT polarization analysis and generate plots like these, where you can see sort of fascinating images of fascinating properties of polarized images and see what we were on about. Anyway, we're way over time. I should end. And so I think, Paul, it's back to you now, right?
And last, Daniel.
George.
Yeah, I think George is gonna to actually end up this talk. Yeah.
All right.
Yeah. So this is just a really quick summary slide. We covered this pipeline in very quick detail. As Ben said, a lot of these codes are quite complicated to use. That should not scare you, but you should approach these tasks with caution, and remember that the people who wrote the codes are often very interested in getting other people to use the codes so that their efforts are not wasted. So feel free to contact any of us. Also, we did not mention that there are semi-analytic models for black hole accretion flow, so you can just replace the GRMHD fluid step with a semi-analytic model, and kind of say, well, we expect the average state to look like this. So what does it look like? What does an image look like if we use this analytic model? Also, just another plug for VIDA, which is another kind of image analysis thing, and Paul talked about that in the last section. If you now skip forward 2 slides, yep, so we have a list of public resources. These slides are available online. I think this list is also reproduced in the online repository that was linked earlier. But thanks for your attention.
Wow, thank you so much. That was really fantastic and on-time set of tutorials. I really acknowledge all of you for your very hard efforts. So I think that we have some time for some questions and answers. Lindy, do you want us to open up some breakout rooms, or do you want, I think that we have 48 participants, so maybe we can just open up some discussion here. I also see that there are some active discussions in the Slack channel. So yeah, just what do you recommend? I think we are happy to have the conversation in the main room, but I'm also happy to provide some breakout.
Sounds good to me, Razieh. Yeah, especially since we still need a Q&A maybe generally, and we can see how things go. Okay,
perfect. So all the participants, please feel free to ask questions, or if you have any recommendations or whatever, just let us know. We have good time for some couple of questions for now. All right, Jacob, please go ahead.
Yeah, hi, thanks. I have a question regarding this Themis framework. So how is that different from other commonly used probabilistic modeling languages or frameworks such as STAN, for example?
Okay, I'll take a shot at this. So I wouldn't say we're as complete as STAN in terms of PPL. We're really, Themis is particularly focused on EHT type modeling. So this means that we have a limited subset of likelihoods, but they're all specifically tailored towards the EHT. We also don't have autodiff in it. This is something that maybe we can do in the future. We do hook into Stan's HMC, so we have a wrapper that goes between our Themis stuff into Stan's code to do HMC. But on top of that, we have a I don't know if you're familiar, and I hope I'm not just saying words, but Stan's HMC is really good if you want to do local posterior exploration. So you want to really flesh out the single peak. But we find for a lot of these image analyses and modeling analyses for the EHT, we get quite multimodal posteriors. So on top of having Stan's HMC, we have a non-reversible parallel tempering sampler that that scales quite well on HPC type machines and lets us move between different modes quite easily. So we're typically able to, if the distribution is multimodal, find it and quickly move to like the peak. I don't know if that's fully answering your question. It's a bit of a loaded one. We could talk hours.
Yeah. I think there's a couple other elements to this, and one is, there's the sampling side of it, what we call a likelihood often has elements that address systematics. So a common one would be gain reconstruction simultaneously with the evaluation of the likelihood to increase efficiency. So that's just a long way of saying, in addition to sampling, we have specially built likelihoods that are relevant for EHT and ngEHT like problems, VLBI problems. And And then we have a designed architecture that separates off the model specification, the likelihood computation, and the sampling and data management, so that individuals can work on that part of the problem that they're interested in and can most profitably expand, and simultaneously leverage all of the other contributions that have been made. And that's something that, in a general purpose, probabilistic inference framework, you may not have, because it's not been tailored to that specific problem. And an example of that, which I think you heard about here, was the ability to run analyses that make use of ray tracing and radiative transfer calculations natively within Themis, but also it's been connected to all of the major, all of the major ray tracing and radiative transfer codes. And so if you had an idea of a particular system that you were interested in looking at, you would just specify something in that code and then hit go on Themis, and it would be able to start producing results. And I wish it were quite that simple. It never is, but that's the theory.
Yeah, maybe one comment on that. So one way to also approach this problem is to modularize everything such in a way that it can interact together. So I don't know how modular this is. So can you also access subparts from outside and things like that? Because otherwise you always get these huge packages that do everything, but they always lag behind in certain aspects. So for example, auto differentiation, what you mentioned. So for example, if you would build on top of the Stan framework, for example, then you would have that automatically in there. Or another example would be the Julia language, where almost everything is interoperable. And you just take the standard library for auto differentiation, and take the standard library for solving differential equations, and everything just plugs together. And you don't have to implement everything yourself.
Yeah, that's right. So it is modularized in the sense that it's all written in C++. And when we say architecture, we really mean interface design. And so this is how the Stan HMC sampler was brought into it. Right, our samplers have a specified interface, which is very generic, and it's possible then to implement whichever sampler you like. And the same thing for what we would call a model or a likelihood. Autodiff is a little bit harder because that requires hooks through the interfaces, and autodiff on something like a adaptive image generation algorithm gets a little bit, because there's a lot of logic in it, and it's a little bit hairy, but it can be done, and maybe this is a place where we need development. If we had to do it over again, we may not have used C++. We may have used something like Julia, and we may yet, but so we can put a link to the documentation for Themis, which I think is publicly available. So you could take a look at, where it was a couple months ago, I suppose, and get a feel for, whether or not that's really modular or not.
Thank you.
Thank you so much, Henry and Paul. Themis is amazing, actually, according to my experience. So is there any other questions? Please ask questions. That's a great chance that we have such a fantastic, community of experts, and you can just simply ask your questions or whatever. You also see that there have been a lot of discussions in the Slack channel. So yeah, either here or there, or maybe you can also take a look at this. Okay, Brit Jeter, sorry, please go ahead.
Yeah, hi. So there was a little bit of discussion about this in the Slack channel during this time, and I was wondering if someone mentioned that Mac computers have moved to a different type of architecture, and I guess there was a little bit of question about if and how we should react to that, and what type of changes would we need to make to make all our scripts compatible, I guess. Is this a problem we need to worry about, or are we just gonna, or is this a small enough thing that we can sort of get by for the next few years? Thanks.
But I think Greg was actually the person that pointed this out. Was it you, Greg?
So yes, it was. And
Okay.
so the answer, I think, depends on what you want to do. You know, on these new Macs, it has, you know, very similar software to the old Macs. And especially if you use Conda as your main environment, that is mostly available, maybe enough that you can get all the way to EHT imaging. I haven't tried it yet, but certainly they've been, the Conda folks have been issuing progress reports saying that they're doing well. So if that's mainly what you do, and then you don't want to take those exact bits over to a supercomputer someday, which most people don't, then you're fine. It's when you want to build a single container and use it on both your Mac and a supercomputer that it's getting to be annoying. And not that many people do that today. I think probably we should do more of that for better repeatability. So it's kind of a work in progress, and it is interesting, but most people probably won't be bothered by it.
Okay, thank you so much. I thought there was another question, but okay. Is this any other question or comments or whatever? That's just the time to ask it. Otherwise, we just close this part. All right, I think that I don't see any other hands. Thank you so much, everybody. I know that that was a long day, but very productive one. I encourage you to please go to the link to the tutorials that we provided. There are a lot of cool stuff there, especially for those that they would like to help us with the image challenge for the ngEHT. There are a lot of step-by-step guides from experts that you could just go and familiarize yourself with all of the steps. So with that note, Lindy, do you have any other announcement or whatever? If not, we can just let others to take some rest and get ready for the last day. All right, okay, fantastic. Thank you so much for your participation. Have a great rest of the day, and bye, everybody.